Uh, Thank you very much for inviting me, and it was a great attempt at my last name. I have a silent G, which is very confusing. It's actually O's. So today I'll talk to you a bit about oriented posets and a bit about how we use it on cluster algebras. And this is based on work with Emine Yildirim. She's the cluster algebra person in our duo. And you can interrupt me with questions anytime. So, the objects we want to study are ideals of posets. I assume at least some of you would be familiar with it. And our example will be a specific type of poset that's called a fence poset. And it's nice because it's a very simple poset. We have they are indexed by compositions, and for 2, 1, 1, 3, we get 2 up steps, 1 down step, 1 up step, and 3 down steps. And if in general, if we have a composition of n, we get a poset on n plus 1 nodes. So what is an ideal of a poset if you are not familiar with it? An ideal is a subset that's downclosed. So if a node is in, anything below it should also be in the ideal. For example, let's look and count the ideals of these. So we have one empty ideal. Ideals with only one element, they must be the minimums. So x1, x4, or x8. We have 3 of those. And with 2 elements, we can either get 2 of these 3, or we can have x2, x1, or x7, x8. And we can keep counting these ideals. And we get a sequence which we call the rank sequence. And we could also write it as a polynomial, which we call the rank polynomial. Of course, this is just one statistic on the ideals. We can just look at the total number, or we can look at what is in each ideal. So this is counting them with respect to how many elements each ideal has. And why are we interested in these ideals? Specifically, why am I interested? So this started with some recent work by Moriarty and Ovsianko, where they gave a Q deformation of rational numbers. And it was very fun, and their deformation has very nice properties, like there is a convergence property, so they can use it to define Q deformations of real numbers, and then one can move to Q deformations of complex numbers, and etc. And the Q deformations can be seen as the numerators and denominators. They are given by rank polynomials for some fence posets. The coefficients come from the continued fraction expressions. And they had a very nice conjecture that the rank polynomials of these fence posets are always unimodal, and I really like puzzles and conjectures, so I was really attracted to this, and we were able to resolve it with Mohan Ravichandran. And this is also connected to something that I am also interested in, young lattices, and we can see them as intervals in the lattice, intervals corresponding to ribbons or border strips. And there are some conjectures on this lattice as well, like when an interval gives a unimodal rank polynomial. So that's one avenue that this could extend to. And then there's Markov numbers, which are a recent interest. They're actually an old-fashioned kind of mathematics. You are just looking at integer solutions of a polynomial on x, y, and z. And there is a 100-year-old conjecture called uniqueness conjecture, which is also a very straightforward conjecture to state and very fun to play with. There are also some connections to cluster algebras, which we'll talk a bit about today. And lastly, there was Moriarty and Leclerc's paper. They used this Q deformation, and they gave a Q deformation of PSL2. So now they were deforming matrices. And they also had some nice conjectures there. And I also started playing around with matrices. So that's how oriented posets came about. And this is a very, very simple combinatorial object that I was able to get a lot of use of. So I hope you guys would like it as well. So an oriented poset is basically just a poset, but we take two special vertices, a left and a right vertex, or you can say a source and a target vertex. And the reason we do it is, then we can connect two such posets to get a larger poset. For example, here we have an oriented poset P, and here we have Q. And we want to connect the left end of Q and the right end of P. And we can do this two ways. We can either say, okay, XR is bigger than or equal to YL, which would give us this poset. Or we could do it the other way. And then we get a larger oriented poset. And this is not specific to fence posets. We could do this with any posets by picking two endpoints. And the fun thing about this is we can describe this operation, at least how this works on the rank polynomial level, with 2 by 2 matrices. And the entries are just given by the rank polynomial with respect to some constraints, like XR is in, XL is not in, that sort of flavor. And then what happens is multiplying these matrices gives the matrix corresponding to the connected piece. And here is like what they look like in general. And if we know these matrices, we know the rank polynomial. It is either the top left one or the sum of the entries in the top row. And one more fun thing, if we take the trace of the matrix, that does act like connecting the two ends of the poset with each other. So when we take the trace, we get the rank polynomial of the circular poset. Like it is generally a poset, not in every case. And in particular, if we have fence posets, it is very easy to get their rank polynomials this way because we only need two things. We can describe them all with up steps and down steps. So we only need to use these two matrices, the up matrix and the down matrix. And then we multiply them. We look at the top left coordinates, we get the rank polynomial. So this was the idea, and we were able to use it to resolve some conjectures and get some identities. And then we met Emine and we started talking about cluster algebras because they also have connections to these fence posets. And we were thinking about what we can do together. And now I will give you a very, very minimalistic introduction to cluster algebras. Like if you do not know cluster algebras, you will not learn with my introduction. If you know it, it's going to be very embarrassing for me, but we'll give it a try. We'll spend a few minutes on this. So cluster algebras were very recently introduced in the early 2000s. Well, it's been 25 years, so maybe not that recently, 20 years ago or so. And they became very popular. And how they work is, they come with generators called cluster variables, and they are grouped into subsets that are called clusters. And you can use mutations to move between these clusters. So to give you an idea, for example, we can have an initial cluster and we have mutation rows. So we can mutate at coordinate 1, 2, or 3. And if we mutate at coordinate 1, we move on to this one. And if we mutate again, we move back, and we can keep mutating. And we can keep getting new clusters. And it could either be a finite or an infinite process depending on what you start with and your mutation rule. And the entries that come up here are all the possible cluster variables, and these are the clusters. And you might notice that all these variables are polynomials divided by these elements of the initial cluster. And there's a general thing that's called the Laurent phenomenon. So if we take any cluster variable, we can write it as a Laurent polynomial in terms of the initial variables, or actually in terms of the variables of any cluster that we fix. And what we are interested in doing is calculating these polynomials. But the setting I'm working is actually more geometrical or topological. We start with a surface, and the surface has some marked points. They might be on the boundary, they might be inside, there might not be a boundary. And then we have a triangulation of the surface. That's called an initial triangulation. And then we draw curves on the surface, connecting two marked points. And we consider them up to isotopy, which you can think of as like we are doing minimal crossings. And for the purpose of this talk, we'll have three flavors of curves. Regular curves, just start from one point and end at another marked point. Then we can have closed curves, which have the same starting and ending point. And then we can have notches, which means that we have a marked point inside and we are wrapping around that point. And this has an associated cluster algebra. The initial triangulation corresponds to the initial cluster variables. And then you can flip arcs to get other triangulations, which is the mutation operation. And these curves you can draw, they correspond to the different cluster variables you can obtain. And our task with Emine was, like, given a curve, we want to calculate the corresponding cluster variable in terms of the initial triangulation. And I was talking to Emine and trying to understand how she does this operation combinatorially. And what was used by her, and I guess it is a very common combinatorial tool in the area, is snake graphs. When you are given a curve, you draw a graph called the snake graph. For each crossing of the curve, you get a box, and the way you orient the box depends on which way the triangles are pointed. And then you look at all the perfect matchings of this snake graph, but you do not get to use the diagonals, just the corner ones. And you turn these numbers into xi's, and then you multiply them, you get a monomial for each perfect matching, and then you sum them up. And then there are some more details. You actually divide by crossing ratio, but that's the general combinatorial thing you do. You count over the perfect matchings of a slightly large graph. And
Well, let's see. I guess I'll send her an email. Well, I think she knows she's gone now.
Maybe she'll pop back up in a second.
This is the most internet trouble we've ever had at AlCoVE, I think.
I think it's because nowadays everybody's traveling again. So we're all in locations. Like my internet also not good. It's just like in a like bad internet connection in Serbia. Like Matt was in Colombia, and who knows where Ezgi is right now. The irony is that my internet connection is bad right now. This one's drastic. Did you send her an email, Oliver?
I emailed her, but like she knows she's not on Zoom, presumably, because
Yeah. Who
yeah,
knows? Maybe she's still giving the talk.
she's not giving a talk to her computer.
I remember in pandemic times making it a few minutes before I realized that I had lost everybody.
I mean, that could be the case if she's in full screen. I mean, I know there's like the green ring,
Yeah.
but she
It
may
logged,
know.
it logged her out. So I think everything would collapse on her, right?
Yeah, she is in Turkey because she just told us that. And if she doesn't have internet, she won't get an email. So I was wondering if anybody had a mobile number for her.
Well, I get email on my phone even when I don't have internet through the data plan.
I
I don't
also
have.
text through the internet. So.
Does anyone have her phone number though?
Oh, bummer.
That's
She's back.
Hey, my apologies. I
Yay.
had some connection issues. So, any questions for me that you guys thought of while I was missing?
we were too busy trying to figure out how to get you back again.
Okay. Well, so these things already come with a bijection to Posets. So this was known, but there wasn't a way of actually calculating the coefficient using the Posets. But we thought, like, if we use the right labeling, then the ideals should give the actually this variable. And happily that worked. So we were able to just look at this triangulation and curve and then get the labeled poset. And then what happens is we look at all these ideals, we look at the generating function, we plug in these labels, and this gives us what we want. Up to some things that we need to multiply it by, like an initial monomial, and we also divide by crossings. But again, the calculation-wise, this is what gives us the different terms. And we were thinking, can we use oriented posets to do this in a fast way? Because for this, we need the generating function, but oriented posets only count the number of points. But that actually was very easy, because the oriented posets, the idea is based on just inclusion-exclusion. It doesn't depend on like which statistic you keep track of. You can just change that. And in practice, like if we want to get all ideals of this connected poset, instead of queues, we just write the labels for each vertex. And then we do the multiplications. And we call this a weight matrix to differentiate. And then you can look at the top left entry, and then voila, you get the generating function of all ideals, which is not fun to count by hand. So this was nice that we had the matrix formula. And we can also do it in other settings. So when we have these small loops, then we use another looping operation in addition to these matrix multiplications. But we again look at the top left entry, then we plug in the weights and multiply by these coefficients. And then this is the sort of thing we get that we were looking for, this expression for the cluster variable of the curve. And we can do this for these kinds of curves that we were discussing. For regular curves, we only need the up and down matrices. If we have closed curves, then we again use these matrices, then take the trace to connect the endpoints. And then with notches, we need this extra gluing functions. But like one can also do other stuff. One thing this we did with Mohan again and Cem Yalım Özel. We were working on chain-link polytopes, like a fun family of polytopes, and they had posets which were sort of stretched in one direction. And for this, we just use these extra matrices correspond to box pieces. So for an A by B box, you define this matrix and you add it into your calculations. And one could also do more connections. So my matrices, they have one left and one right endpoint. You can have 2 of each, 3 of each. You could have different numbers of each. And in general, the matrix grows exponentially. But if you also assume that you are going to have a chain, then you can get by with just k plus 1 times k plus 1 matrix. So for having 2 connections, we need 3 by 3 matrices. And then you can again multiply the matrices and everything works just as they do in the case of one connection. And we are at the moment applying this to higher dimers. They are like perfect matchings on snake graphs, but you match each point n times. For example, here you look at matchings where you match each point twice, and in the poset level that means 2 rows of posets, and you can match each point m times. That would give you m rows, and then we get to use these matrices to do the calculations for these cases as well. This we are doing with Emine Yıldırım and my undergraduate student Erdem Efedelen, who's very talented. And we are also working on extending this to more generalized cluster algebras like orbifolds. This is with Esther, Elizabeth, Vonu, and Emine. And another goal of mine is to use this connection to work with Markov numbers, because there is this connection between Markov numbers, the solutions of the equation, cluster algebras, and Fans posets. Like here, you can see that like you can look at the tilings of the space, and then you can do mutations on that, and each mutation also gives you a triple of Markov numbers, and you can also have generalized Markov numbers, which correspond to different tilings. Some of them correspond to orbifolds. You can do Q deformations. So lots of fun stuff. And this is it. Thank you for staying in the line.
Thank you. Clapping is so disappointing over Zoom. Questions for Ezgi?
I have a question.
Go ahead, Sam.
Nice talk. Sorry about the technical issues. So going back to the original kind of conjecture about unimodality of the rank generating function. So the posets you're looking at are like a special case of intervals in Young's lattice.
Yes, you can think of it like that. They are
And-
like the intervals correspond to the ribbon tableau.
Right. And I believe that it was maybe Dennis Stanton who first observed that like not every interval, okay, yeah, you have
Yeah.
sort of something related to this.
You're fully informed, yes.
So I was just wondering, do
They
you,
are mostly unimodal, but not all of them, and there's a conjecture. I think if it was not solved sometime last year, it should be still open. They think that all self-dual ones are unimodal, but like if you take a random partition, it is highly likely that the interval is unimodal. There are less counterexamples to that. There are counterexamples, but you mostly get unimodality.
okay, so I
I
guess
interrupted your
it's
question.
kind of random, like you can't predict or classify when you do or don't have unimodality.
No, like this conjecture gives a classification, but it is not a very strict, because you get a lot of non-self-dual unimodal cases as well. Like one result of our work with Mohan was that we were able to show polynomials corresponding to ribbon diagrams are unimodal. And we were also able to show the unimodality in this case of chain-link posets, which can also be thought of as a slightly larger family that we have unimodality for, but yes, it will be fun to work more on that and look at more intervals. And I think this might work well with having more connecting points as well. So like looking at a way to dissect a Young diagram into different chains and then try to play with them and get unimodality.
Okay, thank you very much.
Other questions for Ezgi? Okay, well then I have a question. So this is following up on Sam's question. Another way to think about where the fences come from is that they're orientations of the type A Dinkin diagram. And you can look at orientations of the other Dinkin diagrams, and do you know what happens there?
Well, yes and no. Like we worked with, like the first idea was to look at the type B and type C and type D versions of these objects in the cluster algebra, like in AlCoVE representation sense, because that's what I used to do. But algebraically, when you look at other types, you sometimes have a different combinatorial structure. So here, for each vertex, you either have it or not in any ideal. So the algebraic, the sub-representations actually match the ideals. But if you look at other types, then in some, when you look at irreducible representations, you have to put k squared or k cubed in the place of some vertices. So the irreducible representations get a bit more complicated. And if you want to explain them with posets, you have to do some inclusion exclusions. And at least my personal opinion was that posets are just not a very good model if you want to translate this to other types, at least in the AlCoVE representation and this orienting the Dinkin diagram sense. So we tried, we didn't like what we were getting, and then we pivoted.
Nikita Borisov had a question a while back in the chat, but probably Ezgi can't see it because she's had to rejoin the Zoom.
Oh, yes. The question was whether these M matrices are related to Hecke algebras or Demerzer-Lustig operators.
Oh. Yes, I don't think I can give a good answer to that, so I'll pass for now for that question.